Hello, welcome in video 34 in the lecture Advanced Mathematic Modeling. So in the last two videos I showed you examples of super diffusive random walks in very different systems. So walks where the mean square displacement didn't scale as the square root of time. Now in this video I want to reflect a little bit what can be reasons in order to find such non-diffusive behavior. So, but first let's write this down. So let's say we have a random walk, and we have here the expectation of the mean square displacement. We take the square root of this as a function of time. So, and then typically we will find that this mean square displacement goes with t to an power x, t to an exponent alpha, right? Maybe only after a certain transient. We have seen this short-range correlated walk, or maybe only until a certain time, until we have saturation, as we have seen in the DNA walk. Yeah? And then we say if alpha equals 1 over 2, then we call this diffusion. And this is the behavior we should expect, and the central limit theorem tells us if everything is normal, if the increments of the walk are independent and uncorrelated, we should have a diffusion, because we sum up just random, independent random numbers. But then I've shown you examples where this alpha was larger than 1 over 2, and this behavior we call super diffusion. This means the walker on average is able to increase or further away with time than with diffusion. So let's say if this is the typical distance that, let's call it like this, that the walker can have as a function of time, or maybe just, we should have just plotted here x, as the position x. And we have our random walk, you know. And so diffusion means, so the position of the walker is basically determined by this envelope. And now if we have a super diffusive behavior, the walker is able to increase further, either in plus or minus direction. So the typical distance that the walker can have at a time t, so the typical, maybe call it like this, the distance the walker has at time t is can then be larger than the square root of time if we have super diffusion. Yeah? And so how possibly can it be? Because like when we have this long range correlation, so we have a larger chance that we have increments in the same direction, and then the position of the walker can increase further because we have less chance to revert the previous increment. And okay, but there is also the case that this alpha is smaller than 1 over 2, and this is called sub-diffusion. And this is a walker which has smaller distance, so basically there is a lot of anti-correlation going on. The walker doesn't really come so much forward in time, is more centered around 0. So these are the three cases that we can have. And now the question is, what could be the reason for a system to be not diffusive, but to have such anomalous diffusion, either super or sub diffusion? And here, in order to see this, what can happen, so let's look again at our formula when we calculated the second moment as a function of time. Yeah. So we have seen this goes n times here the variance of the increments plus here the sum of the ei times ej if I not equal j. So that was the general formula that we derived. Yeah? And now, so we see now two possible things what can happen. So the first case we have seen before. So if this correlation sum, yeah, if this is diverging, yeah, so reasons or mechanisms, let's call origin of anomalous diffusion. So two things can happen. So either this correlation sum, I write it directly like this, so assuming we have here a stationary process, this depends only on the time distance tau, and we have the autocovariance function. If this decays basically as a slow function of time, basically as tau to, for example, as a power law. But it could be also some motivated, some modified function. For example, it could be a power law times some other function of tau, which is slowly changing with tau. But basically, it decays also with the power law. Yeah, and then. Yeah, so like then we have here a contribution of time n from the second term, which cannot be neglected, and this we have seen in the example of the this groundwater model, that this gave then to gave rise to super diffusive behavior. So the first case is that we have long-range correlations. Correlations should be a bit more careful when I write here. Long-range correlations, and this can be one origin. But what is with the first term? So you think, what could possibly happen? I mean, the time dependence is only in t in here in this n here. So I mean, that's basically the term which is responsible for the diffusion. So what can possibly go wrong here? But the thing is, what's happening if the second moment, let's write it like this, is equals infinity? So I mean, the second moment doesn't exist. And so we will see examples of such distributions. So if we have a distribution which doesn't have a variance, where the second moment doesn't exist, this term here diverges, and the whole calculation doesn't make sense anymore. Yeah? And in such cases, we can also find super diffusive behavior. And so that's basically the second mechanism that can arise in order to give anomalous diffusion. Hey, but what's what's with the central limit theorem? Okay, let's look at the central limit theorem, because this told us, hey, the mean square displacement should go here. The variance of a sum of random numbers should go proportional to time. So we should have basically diffusion here. But this central limit theorem assumes that these two moments exist, that the second moment and the first moment exist. But if these moments are infinite and don't exist, and this can happen. Remember, I told you expectations values are integrals, and these integrals might diverge, and so expectation values might not exist. Yeah. And then if these two expectation values do not exist, this whole central limit theorem doesn't hold anymore. And then we don't have here this our Gaussian distribution of the of the walker, and we don't have the diffusive behavior. So now we want to look a little bit what's happening if we have random walks where the increments have moments which diverge. But before we do this, maybe let's have a first intuition how the walks that we generate in these two cases might differ. Just if we look at them or by just visualize them. Here. So let's say we have long-range correlations. And we want to look what's the typical profile of a random walk. Yeah? And you know, like we have this rough profile, but since the increments are correlated, there is a good chance that we have here long strikes of time intervals of repetitions where the increments go in the same direction. So we have here persistent interval. Maybe then we have inversion, and then maybe we go down again, and then maybe we have here something like this. So we have here persistent intervals, because due to this long-range correlation, and then yeah, in this way suddenly we can increase to higher values. But I have also to say one has to be very careful with these analogies, because like by looking at this you usually will not be able to see if the walk is long-range correlated or super diffusive or not. You have really to make the analysis, because if these persistent intervals would always have the same length here, then you just would have, but then, you know, we go a certain time up, then we go a certain time down, another time up again, and these changes would be random, then we would have again a diffusive behavior on a larger time scale. So we find this persistent interval, so if we have long-range correlations, but these correlations will be on all time scales. So like, or let's call it like this. So we have this persistent interval, yeah, and then we have something else, and we have the next persistent interval, and then we maybe here again. And if we now look at this increment, at this position here, if we have long-range correlation, then the question if we go now up or down at this one point here will depend on what increment we had here thousands or many time steps before, because the memory is over a long time. Yeah? So you cannot directly see it by eye, but basically the idea is that you have persistent intervals which then kind of stretch the random walk, that you have higher displacement. So, and what's then in the other case? Let's say we have second moment doesn't exist. I mean, how can the second moment not exist? I mean, this means if you have at least sometimes very large increments. And let's directly write it here like this, that we have rare large increments. And we will see this very soon in the next videos. So how does the walk look then? Now basically we don't need long-range correlations, so the increments can be uncorrelated, yeah, and let's say very often maybe we have here small increments, but then suddenly we have also larger increment, so we have a jump in the time in the random walk here, and then maybe we have a jump going here. Yeah. So we will see such jumps. Yeah? And such jumps we will need because we will need to have very large increments. Only when we have very large increments the variance will go to infinite. But the jumps cannot always be large because then you just could rescale everything. So the typical behavior will be that most increments are very small. So you see basically here only very small twiggling, but then rarely this large jumps. Yeah? And so if a random walk looks like this here, then probably here we have the problem here in the first term. If the random walk looks more like this, with this kind of persistent intervals, maybe we have long-range correlation. Yeah? So that's kind of two very different mechanisms which can lead to super diffusive behavior. And now let's have a look at this example in more detail. But this we do in the next video. Thank you.